In the next lecture, we want to talk about electromagnetic radiation some more. And specifically, we're going to talk about something called a blackbody. Now, a blackbody is an object that emits or absorbs all the frequencies of electromagnetic radiation over some range. And so there's no gaps or holes in the frequencies of light that are emitted. And of course, remember, when we talk about frequencies, we know that means colors. And so if you think of the sun, you know the sun is really, really hot, so hot that it's actually emitting visible light. And if you take sunlight, so imagine you have some sunlight coming in, and you pass it into a prism, what you get is the light spreads out into all the colors of the rainbow. And so you've got red, orange, yellow, green, blue, indigo, and violet. So those are all the colors of the spectrum. And so that would be an example of a blackbody because all the different colors are there. There's no gaps. Now, if I take hydrogen gas, and if it's very, very thin dilute hydrogen gas, and I heat it up, the hydrogen actually only gives off some colors. It doesn't give off the entire spectrum. And so hydrogen gas would not be a blackbody, but the sun is a blackbody. It gives off all the different colors. Now there's a rule that we're going to talk about later that says good absorbers are good emitters. And so if something is able to give off all the different colors, it's going to be able to absorb all the different colors. Now, it's a weird name, blackbody. Why would they call it a blackbody? A blackbody is something that can give off all the colors or it can absorb all the colors. And so we have this great image from your textbook which illustrates a blackbody in action. So let's look over here on the right. You can see this white box. It's got a lid and the lid's been lifted so you can see inside, and it's completely white. And there's this hole here, and you can see the whiteness of this wall through the hole. So what happens when you close the lid? Well, you can see that that hole, you would think maybe it would be white, but it's not. It's actually black. And so what's happening is that the light coming into the hole is not reflecting back out of the hole. It's being absorbed. And so all the light going into the box through the hole is getting absorbed inside the box. And so what you see is that nothing gets emitted back out. And so you see the absence of color, the blackness. And so that is a black body. Now, we can see over here how this is happening. The sunlight's going to be coming in at every angle, and what happens is on the interior of the box, it reflects like a mirror and it just sort of bounces around inside. And so it doesn't really have a chance to bounce out of the hole. And so the light coming in gets trapped. And this is how you can actually make a blackbody. Now the blackbody, here's what's tricky. The blackbody isn't the box, it's the hole. The hole is what the blackbody is. Now imagine this were some, not made out of wood, but made out of something that you could heat up really, really high, like thousands and thousands of degrees, like the temperature of the sun. Well, if you could heat it up that hot, the inside would start emitting light the way that the sun emits light. And the radiation would come out of the hole, and that radiation would look like the sun's radiation. There would be no gaps. It would be a blackbody. Because if something is good at absorbing all the colors, it's going to be good at making all the colors. If something is good at making all the colors, it's going to be good at absorbing all the colors. Now, interestingly, and you don't really need to know this, it's just kind of an FYI kind of a thing. I mentioned that if you have like a dilute hydrogen gas, not a whole lot of hydrogen, but just, a very thin rarefied gas of hydrogen, and you heat it up, it would only give off certain colors. Well, if you pass white light through that gas of hydrogen, it's going to absorb colors. But it's not going to absorb every color. It's only going to absorb the colors that it would give off if you heated it up. It's kind of weird, but that's just how nature works. Now, here you can see 3 different graphs of blackbody radiation curves. So I've got 3 different blackbodies. What's different between the red curve, the green curve, and the blue curve is the temperature. So the red curve is at 1600 Kelvin, so it's at a relatively low temperature. The green curve is at 2400 Kelvin, so it's a higher temperature. So you notice a few things about the green curve compared to the red curve. First of all, it's at a higher temperature, we know that. But we can see that it's higher, it's bigger, and we can also see that the peak occurs at a higher frequency. Remember, here are the axes. We've got the vertical axis is radiation intensity or brightness. And so we can see that the red here is over at this brightness, the green is over at that brightness, the blue is way up here at this brightness. The higher you go up, that is more brightness. And so we can say that the red light being given off is less bright than the green. The blue light is the brightest of all. Now we can talk about the peaks of these curves, and the peak is where they're the highest. So here would be the peak of the red, here would be the peak of the green, and here would be the peak of the blue. And here's the thing. Each peak corresponds at a particular frequency. So this peak corresponds to this frequency, this peak corresponds to that frequency, this peak corresponds to that frequency, whatever it would be on the graph. Now over here, you can see where visible light is. Visible light corresponds to these frequencies, and so you can see this guy, he'd only be giving off light that's not visible. The green one is giving off a little bit of visible light, but not so much. It's not very bright. You can see the brightness is very low. The blue one, however, at the higher temperature, is giving off much more of the visible light. And so you can just sort of see that's the light being given off here. Now the peak over here where it's brightest, that's not in the visible part of the spectrum. It'd be in the infrared or something like that at a lower frequency. The next thing is what's called Wien's displacement law. Now, Wien was a German dude, so the W in his name is actually pronounced the German way, which means it's pronounced like an English V. So this is Wien's displacement law. And the displacement is talking about how the peak of the radiation is shifting as you get to higher and higher temperature. So the peak is displacing over to the right, the higher the temperature you go. What Wien's displacement law tells us is that the temperature of an object that is emitting blackbody radiation is equal to this constant, and you don't need to memorize this constant, but it's 963 times 10 to the minus 14 Kelvin per Hertz. Hertz is the unit of frequency, Kelvin is of course the unit of temperature, times the frequency in max. And so the Hertz here is going to cancel the Hertz of the frequency. But what's this F max? That's the frequency of the peak. And so right here I could go down and measure the frequency of that peak. I could find the peak here and go down and measure the frequency of that peak. That's F max. It's the frequency of the peak of the radiation. And so the temperature of the object making electromagnetic radiation is equal to this constant times the frequency max. This is one of the coolest things in this course, and it might not be obvious that this is cool, but let me tell you why it is. Let's say you're looking at the light from a star that is millions and millions of miles away from us. You could never go there with a thermometer to measure its temperature. But we know how hot all the stars are in the night sky that we can see. We can measure how hot they are. How do we do it? Because like our sun, stars are black bodies. They give off this kind of characteristic curve where all the frequencies over the range are given off. And so when you have a black body, this rule applies. Now we can't go to the distant star and put a thermometer in it to measure its temperature, but we can measure the light given off and figure out which color is the brightest, which frequency of light is the brightest, and that would be the F max, the peak of radiation and the frequency that corresponds to it. And so by measuring the light from a distant star and finding where the peak frequency is, the frequency that corresponds to the maximum brightness, we can plug the number of that frequency in here, multiply it by this constant, and that tells us the temperature of that star. That is pretty cool. Without going millions and millions of miles away, we can see what the temperature of a star is. Maybe I'm just nerdy, but I think that's really cool. So here's a quick little example. If you measure the sun spectrum, and like I said previously, the sun is an example of a blackbody, the frequency, which is the brightest light for the sun, occurs at 5.95 times 10 to the 14 hertz. Now, how you measure that doesn't really matter. All you need to know is that it's actually not hard to measure that. It's pretty hard to measure some things, but that's not one of them. We can measure the frequency where the peak is. And so if we know the frequency of the sunlight that's brightest, the color that's brightest, in other words, we can plug that number into our formula for Fs max and multiply it by this constant, and we get the temperature of the surface of the sun is 5731 Kelvin, or about 6,000 K. So without even going to the sun, we can measure how hot the surface of the sun is, which, again, pretty darn cool. Now, the next thing we want to talk about is what's called Kirchhoff's radiation law. And there are more complicated ways of saying it with more detail, but the basic idea of Kirchhoff's radiation law is very simple. Good absorbers are good emitters, and vice versa. If something is good at emitting a particular frequency or wavelength of light, it's going to be good at absorbing it. Now, for a blackbody, it's good at emitting all the frequencies over a range, so it's going to be good at absorbing all those frequencies over that range. Now, here we have two pictures, and one of them is painted black, and the other one is polished and smooth, and it's silver and reflective, say. And you put water in it at the same temperature. Say you're making some tea, you boil some water, you put the hot water in each pitcher, and what you find out is that this guy is going to cool off at a different rate from that guy, because everything with temperature is radiating, but the black one is going to be better at radiating than the silver reflected one. Because think of, if this is like a mirror, if it's silvery like a mirror, if sunlight comes in, it's going to be reflected. It's not good at absorbing. Whereas the black, the sunlight comes in, it gets absorbed. And so that's going to make this one heat up faster than that one. Same thing, if it's good at absorbing, it's going to be good at emitting. So if you just put the hot water in, this one's going to emit radiation better than that one, because good absorbers are also good emitters. This one's going to emit radiation better, and that means it's going to cool off faster. There's kind of a classic demonstration of this called a Leslie's cube, where you have a cube, and you can, I don't know if you can see it here, there's kind of a spout here that you could use to fill it with hot water, or you could pour some cold water down there. And this side is silvered, and this side is black. The other sides are usually other colors. And you can actually measure the temperatures of the different sides. And even though the water inside is all one temperature, the temperatures of the sides will be different because they're emitting electromagnetic radiation, but the black side is better at emitting it, so it cools off faster. That's kind of neat, right? Anyway, that's called a Leslie's cube, if you're curious. It's a classic physics demonstration, and it's a really great illustration of this principle.